Hello everybody, this is Mr. Arocena, and on today's video we're going to be talking about electromagnetic induction. So this tells us how we actually generate a lot of our electricity, because we can't always have giant batteries. Alright, so in the last unit we talked about how charges behave inside a magnetic field. So if a charge moves in a magnetic field, it'll feel a force, and we can use the right-hand rule to determine kind of what direction the force is going to go in. Now, because of relativity, the charged particle can actually consider itself stationary, and it can view the magnetic field as the thing moving past it. So in the previous unit we had a charged particle flying through some magnetic field, like so. And then using the right hand rule, we could determine whether how this particle would be pushed. Now, because of relativity, we can actually consider, what if the charged particle is the thing that is stationary, and we have a magnetic field that is moving past the charged particle? Well, this is kind of the same thing as the case presented up here, and both cases result in the charged particle being pushed by a magnetic force. So using the right-hand rule, we can say that, okay, the moving magnetic field will cause a force on stationary charges. So if I move a magnetic field past a charge, I can use the right-hand rule to determine how those charges will be pushed based on the movement of the magnetic field. And this is how we can actually create electricity using a magnet. Alright, so in order to induce the EMF, or to sort of visualize it a little better, here is our magnetic field. So these lines represent the magnetic field. And there's sort of a few ways we can induce this EMF, and that's what we're going to discuss now. So let us suppose we have a wire. Okay, let's say the wire, and we have electrons in this wire, like so. There we go. Okay. If I were to move this wire, or if I were to move the magnetic field in a perpendicular motion, so let's say that the direction of motion is out of the page. So if we use our right-hand rule and we pretend that our electrons are traveling outside the page, actually left-hand rule because we're dealing with electrons. So our thumb would be pointing in the direction of the motion of the charged particles. So the thumb would be pointing towards us. So that would be kind of like this. That's our direction of motion. Our fingers will be pointing in the direction of the magnetic field. So our magnetic field is pointing to the right, so we point our fingers to the right, and the palm will tell us what direction the force is going to be pushing these electrons. So doing this, and again we're using the left-hand rule in this case because we're dealing with electrons, not positive charges. So the force, according to our left-hand rule, the magnetic force is causing our electrons to be pushed down the wire. So all of these electrons are being pushed down the wire. And if those electrons are pushing, I can actually connect this wire to, say, a light bulb like so. And because all of the electrons here are pushing down, they will actually force all of the electrons in this part of the wire to move this way. Because as these electrons get pushed down this way, they come into contact with these electrons, and those electrons get pushed that way. And then the electrons will eventually get pushed throughout the circuit, and then they can actually cause this light bulb to turn on. And all this because we just took a wire and we moved it through a magnetic field. Interestingly enough, we could also say the same thing. If I were to take this magnetic field and move the magnetic field towards us, again, moving the magnetic field towards us is just the same thing as moving the wire towards us. It's just all a matter of your perspective. It would still have the same effect where all these electrons would get pushed. They would push these electrons. They would go through device, and it would turn the device on. Okay, so that's how we can create electricity using a magnet, simply by moving the magnet past the wire or moving the wire past the magnet. And it's really interesting stuff. So looking at this a little bit more, each charge on the wire has some work done to it because it's being pushed along by some distance, and then therefore it gains some potential energy. We can use the work equation, force times distance, to figure out how much energy each charge gains, and we can replace the force with the magnetic force equation, QVB. This is just magnetic force, and then L is the length of the wire, in the magnetic field. Because as soon as the electrons leave the magnetic field, then they are no longer under the magnetic force, so that's how they stop gaining energy, because they stop feeling that force being pushed on them. Okay, so again, this equation here, QVB, that's magnetic force, Q, charge of the particle, V, this is kind of how fast or speed of either the wire, not the electrons, the wire, or the magnetic field, depending on what you're moving. If you're moving the magnetic field, then the V would refer to the speed of the magnetic field. If you're moving the wire, V would refer to the speed of the wire. And again, it really doesn't matter which one you look at, because it will result in the same thing. In some cases, it's easier to move the wire. In some cases, it's easier to move the magnetic field. So what you're moving is very context dependent. Alright, so now here's where, if you remember from current electricity, we described the term electromotive force, and that's basically just voltage another way, or another name. This is kind of where it comes from, because the electromotive force is literally the force that moves the electrons, and as you can see, the electromotive force is created by the magnetic field. And we can actually do a little bit of clever rearranging, because we know that EMF is just energy per charge, and we can use the energy from the previous equation in place of energy, because they're the same, and we can show that the electromotive force is based on just this. So the charges will cancel out. So it doesn't actually, the EMF that gets created doesn't actually depend on what charges are present. It only depends on the speed and the size of the magnetic field, size of B, and the length of the wire. Length of wire. Okay, there we go. So that's how we can generate EMF using a moving magnet, or using a moving wire in the presence of a magnet. Okay. Alright, let's go through some examples of how to work with this equation, or this concept, I guess. So example 1, how much EMF is induced when you have a 25 centimeter piece of wire moved at 8 meters per second in the presence of a magnetic field of 0.5 Tesla? Well, according to our simplifications and substitutions, EMF is V times B times L. So we have a wire, so in this case our wire is moving, but again, it doesn't really matter whether it's the wire moving or the magnetic field moving, it's still the same. We have a fairly large magnetic field of 0.5 Tesla, and we have a 25 centimeter piece of wire, which we will simplify, or at least convert, to meters. Alright, calculating all this out, we have a total EMF of 1 volt. There we go. So if I were to take a 25 centimeter piece of wire and move it at 8 meters per second on a magnetic field of this size, then yeah, we would create 1 volt of electricity. Some of you might be thinking, hey, wait a minute, doesn't the Earth have a magnetic field, and aren't we moving really fast relative to the center of the Earth? Yes, that would actually be correct. If you guys remember from our relativity unit, I always mentioned that if you take your frame of reference to be the center of the planet, then you are moving quite fast. Okay. So let's suppose then that we have a wire and we are moving through the Earth's magnetic field. So we're going to assume that the Earth's magnetic field is stationary. Okay. Otherwise, if the Earth's magnetic field is moving at the same speed as we are, then there's zero relative velocity. So for this example, we're going to assume the Earth's magnetic field is stationary. Okay. How fast would I need to move a 0.5 meter wire in the Earth's magnetic field? Notice the Earth's magnetic field is really tiny on average. Some places it can get to higher than that, and other places it's smaller than this, but this is kind of the average. And we want to induce an EMF of 0.5 volts. So that'll probably be enough to power like a small calculator or LCD display clock or something like that. Alright, so let's calculate that. So according to our equation, EMF is VB times L. We want to generate 0.5 volts. We want to move at a certain speed. The Earth's magnetic field is really tiny, 5.0 times 10 to the negative 5 Tesla. And we have a half meter length of wire. Okay, carrying out the calculations, we get a speed of 20,000 meters per second. So 2.0 times 10 to the 4 meters per second. So if I want to generate half a volt of electricity, I have to move this half meter wire 20,000 meters per second relative to the speed of the magnetic field of the Earth. Okay. So that's really fast. And this is why we can't actually use the Earth's magnetic field to any great effect for generating free electricity, because the speed that we would have to travel relative to the Earth's magnetic field is really, really large. Now the alternative is we simply make a very large piece of wire. So if we make a very long piece of wire, that could compensate for the extreme amount of speed that we would need to be traveling at, but it's generally not cost effective to do that. Yeah, so if you ever hear any claims about people creating free energy using the Earth's magnetic field, it's probably not true. And you can just ask them to show you the calculations, and they probably won't be able to. If they do share them with me. If they do show you the calculation, share them with me. I'd be curious to know. Alright, third example. Let's suppose we have a conducting rod that is 15 centimeters. We're moving it through a magnetic field of 0.5 teslas at a speed of 0.5 meters per second. And we're going to attach the rod to a resistor of 2 ohms. What is the amount of current flowing in this circuit? So here we're going to kind of combine what we just talked about, the EMF of a wire moving through a magnetic field, and Ohm's law from a few units back. Alright, so we'll start off with calculating the amount of EMF, because this will determine how much voltage is present in this particular situation. So we just use EMF is V times B times L. We're moving at a slow speed of 0.5 meters per second through our relatively large magnetic field of 0.5 Tesla, and we have a length of 15 centimeters. So altogether, this situation will generate the following EMF. So I get 0.375 volts. Right. We then attach it to a 2 ohm resistor. So we have a 2 ohm resistor here. And then we can use Ohm's law to figure out how much current we can expect from this particular situation. So we have our that should be 0.375. 0.375. We have an unknown current, and then we have a 2 ohm resistor. So our total current we can expect is kind of small, 0.01875 amps, so we'll round to 0.019 amps with 2 significant figures. So there we go. So that's how we can use our EMF we generate in combination with Ohm's law to analyze this particular circuit. Alright. So that's a quick lesson on, I guess, electromagnetic induction. You can try this yourselves at home. All you need is a magnet and a piece of wire, and then if you have a multimeter or a voltmeter or an ammeter, you can connect it to your wire and just move the magnet around the around it. So like here I'll draw, well, your assignment for today is as follows. Worksheet link will be in the description below. But yeah, if you want to try this at home, all you need is a magnet. So you can have a magnet, have a wire, and attach it to, if you have access to a voltmeter or an ammeter. The ammeter will probably be better, because if you have a good digital ammeter, you'll be able to read really small currents. And you can either move the magnet past it, I guess not so much up and down, probably back and forth through the loop there. Experiment with the motion and see just how much current you can create. Okay, this would have been one of the labs we would have done in class. Anyways, if you have any questions, you guys know how to contact me, and yeah, I'll see you guys later.